Hi guys, and welcome to this video today on using transformations to sketch graphs. Yes, it's a continuation of all the other videos we've done on translations and dilations and reflections and combining them and knowing how to do it all backwards. And this is the next video, so if you haven't watched them, please go back. There's links to the videos coming up throughout this one. But how do we use transformations to sketch graph? Whoa, are you new? Have I seen you before? No? Well, if I haven't, do me a favor. Can you click that red arrow, or the thing the arrow is pointing to, that says something along the lines of show me some support. Subscribers make all the difference to me doing this. It's really quite lonely sitting in this room. Even the dogs abandoned me. You're going to say, what dog? Zero. The dog. He is my mascot. But sadly, yep, now he's gone. Yeah, if you can click that, would be greatly appreciated. Otherwise, let's get on with the learning. And you're going to say, what learning? I'm here to learn. Of course you're here to learn. There's learning with the stuff shown above me. Basically, we've said what you can do forward, you can do backwards too, and know how to take transform functions and find sequences of transformations. But more importantly, you've got to be able to sort of sketch these things, knowing the information that you've given. Now, sketching is pretty much a massive part of methods. Huge part of methods, if I'm perfectly honest with you, because you're going to be sketching graphs for the whole year. Yes, even when we get to the probability stuff, you're still going to be sketching graphs. Too much information. Now, we spend a lot of time dealing with transformations. We've dealt with algebra, and I've spent a lot of time looking at the algebra. There are shortcuts to be able to do this as well, and maybe many people have gone, now I'm just going to do the shortcuts. Much respect to you. But whichever way you use, you're going to have to now start sketching these things. And I suppose one of the important notes about drawing graphs is, for methods and every subject throughout the world that I'm aware of, having taught both in the UK and here, you have to label as much of a graph as you possibly can. And there are certain key points. So x-axis intercepts and y-axis intercepts must be in coordinate form. And by that I mean you cannot draw some sort of a function like this and just put 3 there. All right, it can't be 3, it has to be 3, 0. It's coordinate form. Likewise with y-axis intercepts. Turning points, otherwise known as maximum and minimum. So there are graphs that will have defined turning points, maximums and minimums. Now, this early in the course, if you're over here in Australia doing methods, you can't. We haven't shown you calculus yet, which will show you definitively how to find those. But for certain things like quadratics, you can find, or you have ways to be able to find maximums and minimums looking at completed square form, blah, 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 blah. Endpoints. Now, endpoints are really, really important. When a graph has a domain that's been limited, you must put on the endpoints. Now, the way you show that is doing either open circles or colored in circles and coordinates. You must put those coordinates. Equations of asymptotes and at least one coordinate value. Now, there's arguments over there about what that coordinate value is, particularly if you're dilating something. Examiners need to know that you've understood that something's been dilated, and the best way to show that is using a coordinate. Now, I will probably say that in a number of videos because it's critically important, but let's get into our first example. Identify a sequence of transformations which is mapped 1 on x. So the graph of y equals 1 on x. Now, I always think of that as my base graph. That's what it started was. And there is a number of graphs. There are a number of graphs that are base graphs, and you need to know them. Hyperbolas and truncus and cubics and quartics and all sorts of excellent square root graphs. Very, very important. So it's gone from that to this. So I'm going to write it out slightly larger. Y is equal to 3 on x minus 2 plus 1. Now, I could use my matrix algebra, but I've got to start getting to a point where I can look at these things and know what's happening. So the first thing I'm going to notice is a dilation. And I know that my dilation here is going to be factor 3 from the x-axis. All right, so it's going to stretch that away from the x-axis. Have we got any reflections? No. How do I know if there are reflections? Generally speaking, there'll be a minus value in front of here, but there isn't. So, nah, there's no reflections. And are there any translations? Well, yes, because my x must be replaced with x minus 2, I know I have gone a translation 2 units in the positive direction of the x-axis, and then this plus 1 means I've moved 1 unit up. Now, knowing that is great because I can now use the information to sketch my graph. Now, I tend to build them up in stages. So the first things first, I know what my base graph is. It's y equals 1 on x squared. And that's a pretty ropey graph. That's fine. As a sketch, as a basic, for building up the question, it's fine. I'm trying to get to my final graph, which will be nigh on perfect. What am I doing there? So I'm dilating a factor of 3 away from the x-axis. So the first things first, we've got points 1, 1 there, and minus 1, minus 1. I know this. I also know that I've got asymptotes here and here. All important information. So the first thing I'm going to do is stretch that graph. So that's going to become, well, if it stretches, it's going to look pretty much the same. Let's try and draw it a little bit more accurately. But now I know that this point here is going to be 1, 3, and this point here is going to be -1, -3. So I'm already building up. I've got that one important coordinate point. So there's my factor 3 away from the x-axis. Translations of 2 units to the right, getting it right for my camera, means that, so 2 units to the right. Well, the first thing that's going to move is my asymptote. So that's going to become x equals 2 there. I know this asymptote stays at, y equals 0. And I like having my asymptotes because they effectively give me a guide through which to draw my graph. So there we go. Now, having got that, all I need to do is add 2 onto each of my known values. So that was 1, 3 is now going to become 3, 3. And this was -1, 3 is now going to become 1, minus 3. There we go. So that's my translation of +2. Now I need to move it up by 1. Now, we have to be very, very careful because what do you notice here? We now have a y-axis intercept. I've got one more graph to draw, and that's actually effectively going to move the whole function up by 1. That hyperbola is going to move up by 1. In methods, we have to make sure that we sketch, even though the word is sketch, we have to sketch these properly. And so what I'm actually going to do now is I'm going to try and work out where each of those coordinates will move to help me put them in the right place. Now that's not actually going to stop me scaffolding my graph because I know that my asymptote here at x equals 2 isn't going to change. But what I do know now is that with my graph moving up, my asymptote that was y equals 0 is now going to be here. So assuming that that's now y is equal to 1, what do I know? Well, I know that this point here is just going to have 1 added to my y value. So that's going to become 3, 4. All right, so I can take a guess that that's 3, 4, and pretty much draw this section. So I'm going to write 3, 4 in coordinate form. There are no intercepts to worry about. I'm good. But it's this point here that I now need to be cautious of because that's going to move one place up as well. So it's going to become 1, minus 2. So roughly speaking, that's going to be about here. So I'm going to put 1, minus 2. But what about my intercept? Because this intercept here is going to move. It's going to move up by 1, but I don't currently know what it is. Well, how am I going to find that? Well, I have to go back to my original function, which seems weird, really, because we haven't transformed it in. We haven't put those things in. But if I go back, I had 3 on x minus 2 plus 1. So we had y was equal to 3 on x minus 2 plus 1. Well, to find this intercept, what do I need to know? Well, I know that the x value is 0, so when I put x equals 0 in here, so we're going to say let x equal 0, so I'm going to get y is equal to 3 on minus 2 plus 1, so y is going to equal to minus 1.5 plus 1, which is minus a half. So we now know the y-intercept is minus a half. So I'm going to put across there, and I'll put that coordinate value back in. And there we know that point's going to go, but does it actually have an x-axis intercept? We don't actually know whether this thing is going to cross my x-axis. We would hope it is because it's got to get closer and closer to this asymptote. So now what am I going to do? Well, I need to solve it for when y is equal to 0. So I'm going to have y is equal to 3 on x minus 2 plus 1. I want 0 is equal to 3 on x minus 2 plus 1. Let's scroll it over a moment. So we're going to get -1 is equal to 3 on x minus 2. Multiply both sides by x minus 2 gives me minus brackets x minus 2 equals 3 minus x plus 2 is equal to 3. So take away 2 from both sides gives me minus x is equal to 1. So x is equal to -1. So when y equals 0, x is equal to -1. So we're going to write on there -1, 0. We knew that this coordinate position here was 0, comma, negative a half. And do I have everything I now need? I should go. So I'm now going to make sure that my graph comes up from here, crosses through these points there, and lo and behold, there is the sketch of my transform function. Now, that's fine, not a major issue. It seems like a lot of work, and to be perfectly honest with you, in an exam, can you make sure that your curve is a lot smoother than mine? We can also use a CAS calculator to solve these. By the way, remember, probably beyond this video, it's not an exactly difficult solution. So, example 2, mathematics, and in particularly methods, tries to throw curveballs at you. And I think previously in one of the videos I said you always need to make sure that the x value is equal to 1, or whatever is in front of the x, the coefficient in front of that x is 1. Now, what I've done here is I've thrown a curveball because I've got 2 on 2x minus 4 all squared minus 3. And I've deliberately done it so that x does not have a value in front of it. Now, it has a value of 2 in front of it. Now, the problem here is people will look at this and use the shortcut incorrectly. They'll go, oh no, I know how to do this. I'm going to move it 4 to the right and it's going to go 3 down and I'll have a stretch of 2. Actually, that's not true. The reason being is we want that coefficient of x to be 1. So what I'm going to do is sort of look over here and say, well, I know that 2x minus 4 all squared can be rewritten. I can take a factor of 2 outside that bracket. Now, because we know that ab all squared is equal to a squared b squared, then I know that that can be refactored as 2 squared x minus 2 squared, or 4 lots of x minus 2 all squared. Now, that's useful to me because I've now got a coefficient of x as 1. So I'm going to rewrite this as y becomes equal to 2 on 4 lots of x minus 2 all squared minus 3. And now you can see that things start to change. 2's going to there once, 2's going to there too. So I've got a y is equal to 1 on 2 lots of x minus 2 all squared minus 3. So what does that mean to anything? Well, I can now look at my dilations, reflections, and translations and actually use those shortcuts or the visual things to help me. So dilation, and it's weird because it's not going to be immediately apparent, but actually that's the same as multiplying my function by a half. So I'm now going to have a dilation factor 1/2 away from the x-axis. Reflections, I don't have any. Translations, we now look inside here and I know it's going to move 2 to the right, and I know it's going to move down by 3. Now, in an exam, you would obviously write this out a lot better than that in notation that's acceptable. So we've got a factor away, a half away from the x-axis. Now, what that actually means is actually going to move it closer to the x-axis. All of my values are going to half. So now let's work this out one by one. We've got 1 on x squared. So what does my function 1 on x squared look like? Well, it looks like this because it's a truncus. We know we have an asymptote at x equals 0 and y equals 0. And again, we've got to write on our important points. So 1, 1, which is awesome, and -1, 1, which are important points. And we use these to reference and work out the rest of the graph. So factor away from a factor of half from the x-axis. So it just means we're going to halve all of my x values. So there's my graph. Now, that means that this is going to get slightly closer to the x-axis, and I now know that this point here is going to be 1, a half, and this point here is going to be -1, a half. My asymptotes stay exactly the same because I've not actually translated that graph. And now we are going to translate that graph. We're going to move it 2 to the right. Again, liking this one because hopefully it's not going to be too disgusting to try and work out. Here we go. So there were my asymptotes. We notice that that's going to cross, so we need to just bear that in mind. I'm going to have to find that out. So we're moving it 2 units to the right, so I'm going to add 2 onto each of my x values. So this point here now becomes, that point there now becomes 3, a half, and this point here now becomes 1, a half. Yeah, now my diagram's really squidged together. You will try and make it a little bit better, at least more obvious where those points are. There's my Y and there's my X, but because these are still sketches, not that bothered. Now, finally, I'm going to move the whole thing down by 3. Okay, so moving it up to give myself some room. We now know that the asymptote there was x equals 2. So we've still got my asymptote here at x equals 2. Make sure we label it now because this is going to be my final sketch. I'm moving it down by 3. So let's make it look like I'm moving it down by 3. So we have y is equal to -3. There's x. Oops. There's x. And there's y. And what else do I need? Now I need to draw this on. So let's center this so I've got myself a bit of room. We know that we've moved down by 3, so it's going to be 3 across and 2.5 down. So 3 across and 2.5 down, which is going to put me here. So 3, minus 2.5, and then likewise 1 is going to be 1 across and 2.5 down. So 1 across and 2.5 down. Let's put 1 and minus 2.5. And I think we've got everything we need to be able to sketch this. The truncus is probably the nicest one to be able to draw. So here we go. And yep, I now have to find 3 intercepts. Yeah, because we have to put those onto my graph. So I'm going to do some arrows. No, it doesn't need a Y. Let's try that again. Do an arrow to say that it continues on outside of my graph because I'm not limiting my domain. And now, well, how am I actually going to solve? Well, I need to solve this for y is equal to 1 onto x minus 2 all squared minus 3, and I need to let x equal 0, and I need to let y equal 0. Well, what I'm going to do now is actually use my CAS calculator. So having loaded up my CAS, I'm going to hit main. I'm going to clear my screen from a previous example. Yes, please. And I'm going to load up my keyboard because the best thing to do here is to use my CAS to define. The define function is so important and will save hours and hours of problems, or at least save you having to keep retyping equations in. So I'm going to say let f of x equals 1 on 2, open brackets, x minus 2 all squared, and then we are going to add 3. Sorry, no, we're not. We're going to take away 3. And there we go. Oh, it says invalid syntax, as I forgot to put my equal sign in. That was a noob mistake. And there we go. It says done. Okay, don't exactly know what just happened there. My screen went a bit funny, but we're back. And so, what am I going to do now? Well, first thing I want to do is find out the value when x equals 0. And using my CAS, that is incredibly simple because I just go, what is my function of 0? When x equals 0, what is my value? And out comes minus 23 on 8. That is just gross, but it works for me. So 0, minus 23. So 0 minus 23 on 8. Thank you very much. That was when x equals 0, otherwise known as my y-axis intercept. How do I now find my x-axis intercepts? Well, I'm going to solve for where my function of x is equal to 0 in terms of x. Close my brackets, hit enter, and there you go. Once again, gross values. That's all right, it's not a problem. Now, because this is method, you have to write your answer unless otherwise stated as a surd. So, zooming in on this to give myself some room and make my calculator a little bit more visible, gives me that my value here is minus root 6 on 6 plus 2, 0. And this value here is minus, will be, try that one again, root 6 on 6 plus 2, 0. And there we have it, our completed sketch graph. Now, I don't know about you, it feels like this example has gone on forever. And sadly, yep, not necessarily the most nice way of doing this. But, well, it's the way it goes. Unfortunately, I can't make it any nicer. Now, maths is much more than a collection of boxes. Maths is much more than a collection of boxes, and I think sometimes we do chapters, we get to the end of a chapter, we go, thank you very much, we put all that information in a box, we close the lid, and we shoved it to the back of our brain, only to bring it out when there's a test on that particular chapter, or at the end of the year when we do our VCE or our exam, and then we have to try and unpack all of the boxes and go, oh, I didn't remember this, oh, I didn't know, oh, yeah, much like Christmas. But actually, the problem with methods is that it's not written that way. The examiners will very much, and the textbook very much says, well, don't close the box, keep it open and put more stuff in the box. Start to mix it up, and then we promise you that at the end of the year, you'll be much, much better. Well, what I'm trying to say that is, while we are currently dealing with graph sketching, there is stuff that you're going to need to know from polynomials, from dividing fractions, and all sorts of stuff. So this is a question here that says, basically, show that 2x plus 3 on x minus 1 is the same as 5 plus 2 on x minus 1. Now, how on earth are we going to do this? Well, first things first, you're turning one fraction into 2, and the only way you're going to be able to do that is through division. Now, there's lots of ways of dividing, but because the question says show that, you actually physically have to show it. You have to do the stages. So I'm now going to say, well, 2x plus 3 divided by x minus 1. Now, if you don't know how to do polynomial division, that's a shame because it was done in methods 1 and 2, something you're going to need to recap and learn, I'm afraid. So x is into 2x, go 2 times. 2 times x gives me 2x. 2 times minus 1 gives me minus 2. Subtract them, they go, and I get 5. Now that there is good enough for the show that, because I've now shown, so I can now say, therefore, 2x plus 3 on x minus 1 is equal to 5 plus 2 on x minus 1. So that's normally a 1-mark question. Then it will go on to say, hence, without using a calculator, sketch the graph of this function here that's real but not plus 1. Now, why is it not plus 1? This is our function notation. So do you see what we're doing now? So we've had polynomials with some division. Then we've changed track. We've gone back to function notation. Then we're going to try and put that together with drawing or sketching this graph. And it says, you know, the function of all real values, but not 1. Well, the reason it can't be 1 is because that then would make that 0. And we can't divide by a 0, but the good news is they've now also told me where an asymptote is of this function. Well, I don't know how that's going to look without a calculator, but I do know how this is going to look because they've written it in a funky way, which if I rearrange it, gives me a function I know. I can look at this and say, hold on a moment, that's the graph of y equals 1 on x, which has been dilated that way away from the x-axis factor 2. It's been moved that way, 1 right, and then that way by 5. All right, easy. So quick sketches to see what happens. We have 1 on x does this, and we know that point there is 1, 1, and that point there is minus 1, minus 1. So that's my standard 1 on x. We've got the asymptotes, so I'll put those in a moment. I'm going to times by 2. So drawing this again, quick sketch. That gives me this point here now becomes 1, 2, and this point here becomes minus 1, minus 2 because I've stretched it double away from the x-axis. Shift it 1 to the right. So here's a quick sketch. Now this is where life becomes interesting. So there's my x equals 1 asymptote. My y equals 0 stays the same. Here we go. We've got this, and then we'll end up with something like this. So this point here now becomes 2, 2. And this point here becomes 0, minus 2. Well, that's good. Thank you very much. That's actually giving me a y-axis intercept. Don't have to stress too much about that. And then finally, we're going to move the whole thing up by 5. So give myself a little bit more room. Let's do that. So one of my asymptotes, that asymptote stays at x equals 1, but I now have an asymptote at y is equal to 5. So we need to make sure now that because this is my final graph, I comply and do everything that they want me to do. So I now going to add 5. So this point here now becomes 2, 7. And I know that that becomes equal to 0, 3. Now drawing this gives me this. Thank you very much. Oh, don't do that. Did you notice I just did that flick there? That loses your marks in methods. All right, don't do that. And this one's going to do some. Oh, that was dreadful. This one's going to do something like, let's try to draw it like this now. So backwards, there we go. That's going to do something like that. Well, what do we notice? We have a point here where my y value is equal to 0. So I'm going to have to go back to my original equation. And it was 2 on x minus 1. 2 on x minus 1 plus 5. So can I do this without a calculator? Fairly sure I can. Well, that point there is when y is equal to 0. So we get 0 is equal to 2 on x minus 1 plus 5. Take away 5 from both sides will give me 2 on x minus 1 is equal to negative 5. Multiply through by x minus 1 gives me 2 lots of minus 5 times x minus 1. 2 is minus 5x plus 5. Take away 5 from both sides gives me minus 3 is minus 5 on x. So x becomes 3/5. So zooming in, we know that this point here is 3/5, 0. And what else have I got to put on? My arrows to say that it is going to infinity and beyond. And there we go, ladies and gentlemen. That is my final sketch. And believe it or not, finally the end of this video. It seems to have gone on forever, and my apologies for that, but thank you very much if you're still watching. It's great to see you. All right, it's that time again, so if you haven't already done so, can you subscribe for me by clicking that button? And again, if you can let your friends know, that would be greatly appreciated. You're sitting there going, I'm not letting my friends know, I'm about to lose my friends. Yeah, I understand. Okay, there's a video over there loading as well for you if you would like to watch, but thank you, thank you, thank you. I look forward to seeing you next time. This is MaffsGuru, out. Bye-bye.